So this is the second type of mixing problem, where it's a bit more difficult because the amount going in is different to the amount coming out. So let's have a look at this. There is a 100-litre tank with 50 litres of pure water in it. A solution of 0.4 kilograms of salt per litre is pumped into the tank at a rate of 3 litres per minute, and a well-mixed solution leaves at the rate of 2 litres per minute. So let's have a look at this in terms of a picture. So what you've got is a 100-litre tank. Starts off with 50 litres of water in it. And there is a solution going in with 0.4 kilograms per minute, per litre, sorry. And this is at 3 litres per minute. It's a bit small, but... And the solution going out is a well-mixed solution. So that's the concentration times the flow, which is 2 litres per minute. So the hard bit is, what is this concentration going out? Well, we don't know the concentration in here at any time, so that's the amount of salt in it. It's the concentration, so it's the amount of salt divided by the volume of the tank. Now, so the A is just going to be the same as before. It's A of T. But what's the volume? It's going to be 50 plus every minute there's an extra 1 litre in. So the volume in this case is going to be 50 plus 1T. So that's going to be the concentration. It's going to be A over 50 plus 1T, or 50 plus T. So when we set up our little equation, and it's going to be set up exactly the same way, dA to T is going to be concentration in times flow minus concentration out times flow. Okay, so that is always the same sort of setup to start with, at least. What's our concentration in? The concentration was 0.4 kilograms per litre. This is dA to T, times our flow, which was 3 litres per minute. And again, what we have here is that the litres cancel out, and we've got amount over time, which is exactly what we want. The concentration going out, that is going to be our A of T over the volume. Now, the last time, if the volume doesn't change, that's nice and easy. But in this case, the volume's always going to be changing. It's going to be 50 plus 1T. Okay, 50 plus 1T times the flow, which is 2 litres per minute. And again, this is litres per minute. This is kilograms per litre. And again, they cancel out. It's always a nice check if the units are matching up. So what we've got here is that dA to T equals 1.2 minus 2A over 50 plus T. So that's our equation. Now, the next step is to really think, oh, how do we solve this type of equation? And that's a big part of this course is, okay, now we've got this, how do we go about solving? Which method are we going to use? Now, I can rewrite this dA to T plus 2 over 50 plus TA equals 1.2. And that is in the form now of this integrating factor. So in this case, we're going to use an integrating factor. And I don't want to say that always if there is a difference in the concentration in and the concentration out, you're going to use integrating factor. But nearly everyone, I think everyone that I've seen so far, you use integrating factor. So I'm not saying that's going to keep happening, but it looks like to me you nearly always use integrating factor. So we're going to use this integrating factor. So it's another one of those methods that we have to use. Remember, the integrating factor is going to be e to the integral of this thing here. So e to the integral of 2 over 50 plus t to t. What does this equal? Well, this is going to be up here. If we just look at the integral of this, it's going to be 2e to the 2 log of 50 plus t. Okay? Not sure how we're going with that, but if this was 2 outside of the integral of 1 over 50 plus t, I can see that the derivative of this is 1, so it's going to be the log at the bottom. So, okay. I want to pretty this up a little bit more, so I might write it as e to the log. Remember, if there's a 2 out the front, I can take it up here to the power, 50 plus t squared. Nice thing about this is that these two things cancel out. Because those two things cancel out, our integrating factor is just 50 plus t squared. And if you remember this stuff with integrating factors, what do we do with that? We multiply everything by that. And again, so what we get is 50 plus t squared dA dt plus 2 times 50 plus ta equals 1.2, I think it should be. I don't know where I got 1.5 from. 1.2 50 plus t squared. So I multiplied everything by that. Now remember, the whole idea of this integrating factor is that this is really the derivative of 50 plus t squared a. So that's the whole point of this integrating factor, that the derivative of this is going to be, because this is a product, the first term times the derivative of the second plus the second term times the derivative of the first. And so that's going to equal 1.2 50 plus t squared. And what we're going to do now is the way we do all integrating factor questions, we're going to integrate both sides. So when we integrate both sides, the nice thing about integrating factor is these two things just cancel. And what we're left with is that 50 plus t squared a equals, this is going to be 1.2 outside of 50 plus t to the power of 3 over 3 times the derivative of this, which is just 1. So when we integrate both sides, that's what we get. We plus c, don't forget your plus c. We wanted to know what a equals, so a equals 1.2 over 3. Outside of dividing everything by this, you're just going to get 50 plus t, which is nice, plus c over 50 plus t cubed. And again, what we could do is go back to our initial conditions, and our initial conditions were that we didn't really give initial conditions, so I would leave it there, but in this case, it sort of assumes that at the start there was none, so a equals 0, but when t equals 0, and away you go from there and find c. But I hope that gives you an idea of these two different types of mixing solutions. Thanks. Yeah.